So first we will discuss the solutions for our second homework. So first, let's begin with the first question, which asks, find the generating function of the sequence where AR is the number of ways in which the sum R will show when two distinct dice are rolled, with the first one showing even numbers and the second one showing odd numbers. So this one should be easy for you. So we can have two generating functions and times them together. The first generating function is for the first dice. So we have x squared plus x to the power 4 plus x to the power 6. And the second generating function for the second dice is x plus x cubed plus x to the power 5. And we times them together is the generating function we want. And for the second question, how many different ways are there to color n distinct objects using 3 colors, if every color must be used at least once? So we can use a similar way. So for each color, we have the generating function, which is equal to the first line, which is equal to e to the power x minus 1. We cannot have zero object color with some color. So we times them together, we can get e to the power 3x minus 3 times e to the power 2x plus 3 times e to the power x minus 1. And the coefficient of x to the power n divided by n factorial should be 3 to the power n minus 3 times 2 to the power n plus 3 when n is greater than or equal to 3. So this equation, you can actually also use the principle of inclusion and exclusion to obtain the same result. So for example, this is 3 colors, and this is one. Let me see. This is we are lacking one of the colors, and this is we lacking 2 of the colors. So is everyone okay with the first 2 questions? Okay. And for question 3, we want you to find the coefficient of x to the power r in this generating function. So we give you the hint is to reveal the partial fraction. So by partial fraction, we mean we can have x squared minus 5x plus 6. We can make it become 1 over x minus 2 plus 1 over x minus 3. So and we take negative 1/2 out and taking negative 1 over 3 out, we can get these 2 parts and get the generating function of each of these parts. And here we have x squared plus 1. So if we want to get the coefficient of x to the power n, then we can have the coefficient of x to the power n here, and plus the coefficient of x to the power n minus 2 in here. So we can get the coefficient of x to the power n is equal to the sum of these 4. But when n is less than 2, then you should notice this part, x squared times this part, will not produce x to the power 0 and x to the power 1. So you should not adding these 2 here. So when n is less than 2, we have only 2 of them. So is everyone okay with this part? Yes? No question? Okay. So question 4 is asks you to express the following sum in closed form. So by closed form, we means the number of operations we have is not related to the numbers here. So, for example, because we have n here, so in this form, the number of operations is the larger n is the number of operations here is we need more operations. So for this question, so this is our question. And first, I add 1 to the power n minus n here, and choose n into n factorial divided by n minus n factorial and n factorial. And this, the n factorial here, and this n factorial here, we can delete each other. So we can get 1 times n minus n times w to the power n and times x to the power n here. And we divide x to the power n into x to the power n minus n and x to the power n here and put n here and here. So we can get this, and we have n equal to 0 to n. So this is the coefficient of x to the power n when we times these two together. So this one is e to the power x, and this one is e to the power wx. So we can get is e to the power x times e to the power wx, which is equal to e to the power 1 plus w times x.
I have a different way. So let me show you. I guess some of you will be using the other way. So so we are going to do the summation of n is equal to 0 up to infinity, right? And then the summation of n is equal to 0 up to n. It's okay. Okay, and then what? And then I forget. And then this n choose n. And then this omega to the power n. Am I correct? And then we have x to the power n divided by n. Okay. Yeah, I think okay. And then, okay, if you look at this one, so first of all, this x to the power n divided by n factorial is related to this n. So we can move it here. Okay. And then what's this? This is n choose n multiplied with omega to the power n. We sum up all the terms. So by binomial theorem, this is exactly 1 plus omega to the power n. Am I correct? Yeah, that's it. So we have this term, 1 plus omega to the power n. We have x to the power n divided by n factorial. We want to sum everything from n is 0 up to infinity, right? So that's it. So this is exactly equal to e to the power 1 plus omega n. Okay, so this is another way. So it depends on how you combine the terms. So I'm more familiar with the binomial theorem, so I use that. Simon is more familiar with the E, so he's using a different one. Okay, thank you.
Okay, so for the next question, we ask you to evaluate the following sum in which n and k are non-negative integers. So this should be familiar for you. So if we write it down in the form of sigma sum, then we can have this is actually equal to n choose j times n choose k minus j, where j is equal to 0 to k. So this is the coefficient of x to the power k of when we times 1 plus x to the power n and 1 plus x to the power n, which is 1 equal to 1 to the plus x to the power n minus n. So therefore it should be obvious that the coefficient of x to the power k is equal to n plus n choose k. And for question 6, we want you to find the exponential generative function for the sequence 1, 1 times 5, 1 times 5 times 9, and 1, 5, 9, 13, and 1, 5, all the way up to 4r plus 1 for the r's. So, okay, yes. So first I list all the generative function by brute force. As you can see, the coefficient of x to the power. Okay, here I use n instead. The coefficient of x to the power n here should be 1 times 5 times 9 times all the way up to 4n plus 1 divided by n factorial. And for each term, now I divided it by 4. I taking 4 out to here. So we can get 1 over 4 plus 1, 1 over 4 plus 2, all the way up to 1 over 4 plus n, divided by n squared. Now, I take minus 1 out of length. So we have n minus 1 putting in here. And here we got negative 1 over 4 minus 1 and minus 2 and all the way down to minus n. So as it's a similar question as we discussed in class. This one is equal to negative 5 over 4. Choose n. And here we have negative 4 x to the power n. So this one is the generating function 1 minus 4x to the power negative 5 over 4. So as far as I remember, we have a similar question in class, but yes, this part maybe is very non-intuitive. So there is no real world way to choose n out of a negative number, but yeah. So is everyone okay with this question? Okay. And for the normal questions, first we want you to show that the number of partition of integer 2r plus k into exactly r choose k parts is the same for any non-negative integers k. So we tell you to study the Ferris diagram. So a Ferris diagram is actually pretty straightforward. So a Ferris diagram is a diagram we use to represent how we partition an integer. So for a simple example, if we want to show 11 can be divided into 4 plus 2 plus 2 plus 1, then we draw 4 in the first line, and 2 dots in the second, 2 dots in the third, and 1 dot in the final one. So the principle is we align the dots left, align each dot left, and from the largest number to the smallest number. So this is a Ferris diagram. And so we want you to show that the number of partition of the integer 2r plus k into exactly r plus k parts is exactly the same for any non-negative integer k. So if we want to draw this partition into a Ferris diagram, then we have to draw in r plus k lines. And in the r plus k lines, we already have r plus k dots here. So we only have r dots left in the right hand part. So the remaining we only have to distribute the r dots or partition the remaining r dots to determine the number of to partition 2r plus k dots. So as you can see, this is actually equal to the number of ways to partition r dots, and therefore it's independent from k.
And for excuse me, so does that make sense to you? So first of all, if you have a particular way to partition the number 2r plus k in r plus k parts, then using the Ferris diagram, it must have exactly r plus k rows, right? And then each row must be non-empty. So in that sense, what Simon says is that, okay, so the first column must all be having 1 dot. Okay, so that takes care of r plus k dots. And how about the remaining? So the remaining will be r dots on the right hand side. Okay, so for each way that you can partition a 2r plus k number, then it corresponds to a way to partition the number r, and vice versa. So if you think of a way to partition r, the number r, perhaps r is equal to r plus 0, 0, 0, 0, 0, 0, then it corresponds to a way to partition the 2r plus k, right? And then the clever observation is that the number of ways to partition the 2r plus k numbers in a certain way is exactly equal to the number of ways to partition the number r. So what does that mean? It means that it is independent of k. The number of ways to partition r, you don't have the k there. Okay. So this is so interesting. Yeah? So whenever you have a number, let's say r is equal to 5, k is equal to 3. So the number of ways to partition 13 into 8 parts is the same as the number of ways to partition, let's say this time you take r is equal to 5 and then k is equal to 1. The number of ways to partition 11 into 6 parts. So that's very interesting. The number of ways to partition 13 into 8 parts is equal to the number of ways to partition 11 into 6 parts. And it is the same as the number of ways to partition, what? 12 into 7 parts. Yeah, that's not that trivial if you look at it. But using the Ferris diagram, yeah, this certainly becomes very easy. Okay.
Yes. And question 8 is just a full form question, and you have no formal answers. So it asks why 11 to the power 4 or 101 to the power 6 is easy to compute for us knowing the binomial coefficient. So as you can see, 11 to the power 4 is actually equal to 10 plus 4 to the power 4. And 101 to the power 6 is actually equal to 100 plus 1 times 6. So each digit in the final result will corresponding to, or not each digit, but most of some. In the first case, each digit will corresponding to some binomial coefficient, and yes, yeah, and for this every 2 digits will correspond to one of the binomial coefficient. And if we know binomial coefficient or even the Pascal triangle, so we can easily see 11 to the power 4 is equal to the first row, so it's 1, 4, 6, 4, 1, 4, 1. And for the second one, we can easily see it's equal to 1, 0, 6, 1, 5, 2, 0, 1, 5, 0, 6, 0, 1. So this is just a full one question. And for the final one, surely the following equation is true. So here we have n equal to 1 to infinity, and we have 1 over n to the power s is equal to, we times all of them together, and we here for p is a prime number, so we for all prime number we times them together 1 over 1 minus p to the power negative x. So first we left the left-hand side equation. We use this. I forgot how to pronounce this symbol. Theta is be the left-hand side equation. And as you can see, the dividing part contains every positive integer here, 2, 3, 4, 5. And if we times it with 1 over 2 to the power s, then we can get every number divisible by 2. So if I use this minus this, then we can get 1 minus 1 over 2 to the power s times the theta function is equal to 1, 3, 5, 7 here, which is all the number which is not divisible by 2. And similarly, we can times it again with 1 over 3 to the power s. Then we got all the numbers. Here we got 3, 9, 15, 21, which is all the numbers that is divisible by 3, but not divisible by 2. And then we use this minus this to get all the numbers that is not divisible by 2 or 3. So we repeat this kind of operation with all the prime numbers, and we know that every number must be divisible by at least one of the prime numbers. So all the things left is we will have only one left, which is not divisible by any prime numbers. So we can get the sum of, we times all the case for the prime numbers here, times this is equal to 1. And we put this thing into the right hand side, so we can get the equation we want to prove.
So this result is I think it is very interesting. This is proven by Euler, right?
Yes,
Euler. And then on the left hand side is summation, but on the right hand side is product. Right? That's very, very interesting.
And there's the Riemann
theta function.
Is Riemann or Riemann?
R-I-E-Y-M-A-N. Yes. Okay. So that's it. Okay, good. Thanks. Okay, by the way, so Euler, so yes, this is the so-called Riemann theta function, and then there are a lot of properties of it. And Euler actually get famous by showing solving this problem.